Good afternoon. Welcome. Thank you for coming. So is everyone having a good PDC so far? Yeah? Well, I've decided that the people organizing the PDC really don't like me. They've scheduled my talk at the exact same time as Anders Hellsberg, Raymond Chen, and Chris Sells. Okay? So thank you all for coming, and people at the back, please don't leave because I said that. That's rude. So during yesterday's keynote, Don Box came out and he said, this talk has only demos. Don't show me PowerPoint. And the entire keynote room burst into applause. Today, I'm going to come and tell you that my talk has no demos and only PowerPoint. Boo! No, it's okay. Boo along with me. Boo! Okay. So now that we have got all that negativity out of our system, let's go have some fun. Microsoft has built a ton of services over the last several years. Ray Ozzie came out and spoke about how we as a company have built up a lot of tribal knowledge on how to build these services. We have made mistakes. We have learned from them. And this talk, over the next 1 hour, I will talk to you about some best practices and principles that we have learned, about how Windows Azure bakes these best practices and principles into the platform, and what you can do to not repeat our mistakes. Now, let's get started. I went and spoke to a lot of teams when preparing for this talk, and there was one common theme that I heard from pretty much every single team which was running a cloud service. And to kind of start off, I want to start off with that theme and a story that illustrates that theme. In 1980, this man, Tony Hoare, that's right, the legendary Tony Hoare, the man behind Quicksort, was given the Turing Award for computer science, the Nobel Prize for computer science, if you will. He made a famous acceptance speech called the Emperor's Old Clothes. And in that acceptance speech, he said something which is incredibly relevant to us. He said, the price of reliability is in the pursuit of the utmost simplicity. Simplicity. Even if you remember nothing else from the rest of the hour, even if you decide that I'm boring and decide to go watch Anders or Raymond during halfway across session, I want you to remember this. Keep things simple, and you'll almost always do just fine. I've divided my talk into 3 acts. And in the very first act, we will talk about how you can go about building and architecting some of these cloud services. So here's how the world works. Networks are unreliable. Connections get dropped. Messages may not go to the other side. It's a bad thing. Hardware fails. Your hard disk could lose data. It could crash. Your computer could power cycle. Bad things could happen. In fact, your computer could catch on fire and explode. Above the level of a single machine, even your data center could get into trouble. It could get eaten by a big, goofy, green-eyed monster. Now, I believe Microsoft Robotics has a 500-foot robot that we are building to target this scenario. So, seriously though, when we looked at all this, and as is apparent, we are a negative bunch of people, we have a pretty dim view of how the world works, we had a few design choices in how we could go about building Windows Azure. We could have gone and done something like this. We could have said, hey, here's a big, reliable, expensive machine that's going to last years and years. It turns out that this is a really bad idea for a lot of cases, because after some point in time, you just can't get bigger machines. So we said, instead of building hardware which is reliable, we'll get reliability through software. And we will run that software on several commodity machines. And in fact, not just several commodity machines, lots and lots of commodity machines. Now, this is interesting to us as developers because this presents a few challenges in the way we typically write applications. We don't write applications which run on lots and lots of machines, which once in a while could fail over. That is not just the way we have built apps for years and years. So what are the kind of challenges that we have to deal with? The first is, what do you do about a thing called state, right? Now, to make things concrete, state could be a shopping cart data. State could be the currently logged user. It is pretty much anything that is ephemeral and being tracked by your application. If you look at the way people build architectures today, state is something like this. It's like a peanut butter sandwich where state is smeared all over the application. Some of it is in the client, some of it is in the application, some of it is in the back end. When you're building scalable cloud services, this is a bad idea. Because when you have such smearing, you just can't go add 15, 20, 100, 1,000 other commodity machines to just go scale out your application. You just can't do that because we can't smear the state across. So what we want you to do is to go take that smeared state that you have, go scrape off that state, separate that state out. So you have your application, and you have this gooey little state over here. I see people cringing in the audience. You can thank me later for putting that visual in your head. So what we like to tell people is, go horizontal and go build stateless front ends. Go separate out state from your web applications and go store them somewhere else. So this gives you a great benefit. If you want to scale out, you can just go to the portal or just go add several instances, and you don't have to worry about state being in any of these instances. So you can just scale across. Next question is, so where can I put this state if I can't put it inside my application? Well, you can go store it in Windows Azure storage. So we have highly scalable, highly available blobs, tables, and queues. Go take that state and put it in our storage system. And we will make sure that you can have fast access to it. We'll make sure that it sticks around. We'll make sure that all those good things happen. As a team, as a company, we believe in this. We believe in this so deeply that we made it the default out of the box. We believe in it so much that we even have it tattooed on our backs. If you go install the SDK, and when you go create a file new project, by default, you will see that all the templates that we have go try and push you towards writing stateless applications and going and storing state somewhere else. Now, if you're an ASP.NET developer, the way you interact with state is typically through session state. So what we did is we went and, as a part of our samples, we created a session state provider. That is something which plugs into the ASP.NET pipeline and stores session state inside Windows Azure tables. Now, if you go look at the code here, this is just a blob of XML that you can go stick into your web.config file. And what this will do is to automatically, whenever you do a session.foo, it's going to go take that and store it inside our table storage. So next time when you want to go scale across, you can just do that seamlessly because this state is now stored in our tables. OK, so now we have dealt with state. The next question we have when you're dealing with fairly unreliable hardware is how do you deal with the unreliable components built on top of this hardware? Here's a typical application, right? In yesterday's keynote, you saw Don and Chris write a service. So you could go build an application which could go call one of these services synchronously. Well, guess what? That service is running on unreliable hardware. So it could go down. It will come back up, but it could go down any given point in time. You can't trust it being there. So as a developer, this could be your login provider. This could be some service which is doing something for your application. Now, and this is running on something which cannot be trusted to be up all the time. It'll just go up and come back. So how do you go architect your application to scale out? So the answer for this comes from a place that we are all familiar with, the local Starbucks. Now, I come from Seattle, and we have 1 or 2 Starbucks over there. The Seattleites are all laughing over here. Now, think carefully about what happens when you go order coffee at Starbucks. You go walk up to the cashier, you go give them your order, and then you go off somewhere else to go collect that order. Now, if this were a typical computer science transaction, you would not leave that cashier until you had got your coffee in your hand. That's how we, in computer science, typically think of transactions. But in Starbucks, what happens? The cashier takes your order, you hand him or her your money, they write down your order on a cup, they place a cup in a queue, and a barista over there goes and makes your coffee. Now, this is a classic queuing system, and it has some subtle properties. For example, let us say that barista over there making coffee just topples over. You know, that's an unreliable component. Well, guess what? The cashier can still keep on taking customer orders, just as the queue is going to get piled up. The customers don't see any difference at all. Let us say there's a lot of load on the system. Let us say this queue becomes enormous. You can add 2 baristas or 3, and there is no difference here at all. The cashier doesn't need to know at all. You can do the same thing over here. You can add more cashiers. And the system, this is a classic loosely coupled system. And that is what you should be doing to go build apps, components which talk to each other. Go make them loosely coupled. Go make them asynchronous. If one of them fails, your other component should not go down because that component is having a momentary relapse. Now, we spoke about the Starbucks queue. So the equivalent in Windows Azure, queues from 2 different Seattle corporations, is to go stick those messages in our queue. So you can take that coffee order, go stick in our queue, and we'll make sure that the message gets delivered at least once, and somebody else can go pick it up and do whatever. And here's a synchronous Starbucks application, okay? Imagine that Starbucks was a website, Starbucks Web 2.0. Here's how it would work. You would go to the website, you would say, get me some coffee, and the site would synchronously go process that order, and then give it back to you. And here's some hypothetical code. This is a pretty classic code behind file. You'll see that there's a button click. You say, give me an order. And then there's a function over there which goes and makes coffee, which is obviously something which is going to take some time. Now, I haven't shown that code because it's part of a top secret .NET 4 feature. It's part of the system.beverages.coffee namespace. Now, let's see how we can make this loosely coupled. You have your load balancer at the front, so all these requests can go to any one of your web front ends. The web front end takes the input, the coffee order, and sticks it into the queue. And that's all it knows about the order. And it is done. It tells the customer, hey, I'm done. You go over there and get back your order. The customer can then, the worker process can then go process that coffee order and then hand it off to the customer. Here's how it looks in actual code. Now, notice the difference. Same code behind file, but there is no longer any processing. The coffee making doesn't happen here any longer. Instead, what we do is we go cons up a queue storage object. We go get a handle to the right message queue, and we go take that order and go stuff it inside that message queue. Now, apart from the coffee making part, this is actually real code from the SDK. I mean, this is code that I actually compile. The worker process does a similar thing. It gets a handle to the queue storage, it gets handled to the actual queue, and then sits in a loop, hey, is there a new order? Is there a new order? When it sees something, it goes and processes it, right? So without much effort, we have made the system loosely coupled and scalable. The next issue when dealing with scalable services is how do you deal with varying load? If you are a consumer-facing application, you are incredibly familiar with this scenario. The day Slashdot links to you, the day you're on the Dig homepage, the day Michael Arrington links to you is when you're going to see these spikes, right? and you have to go deal with them. Your application needs to go deal with them. Now, a lot of you may be here wondering, hey, you know what? My application runs inside the firewall. I don't have to go deal with Michael Arrington. And I have a story to kind of prove that wrong. Several years ago, Microsoft, as pretty much every other corporation, had a payroll application. So this was a site where you could go to internally as an employee, and you could see, how much you're going to get paid. The Microsoft performance review would happen around August. And September 15th was the date in which you would see how much your pay increased by. So guess what? Every single year on September 15th, a bunch of very enthusiastic Microsoft employees would go hit that site and keep hitting F5. And the site would collapse every single year. In fact, it got so bad that Raymond Chen actually would send an email to them a week before September 15th every year. Right? He was actually a manual alerting system. Now, in the last few years, they have fixed it. This year, I found out exactly what I was getting paid. But this is a classic example of how even within the firewall, even within the enterprise application, you're going to see varying load patterns. And your application needs to be able to deal with it. The way to deal with it is to go build what I would call a thermostat. Now, I have no idea how real-life thermostats work. But here's how a software thermostat works for me. So you have a piece of code which goes and monitors the amount of load on your system. In Windows Azure, this is as simple as monitoring the number of work items in your queue. Depending on the number of work items in your queue, you see what kind of work you need to prioritize. Right? If your system is under heavy load, you can make sure that the worker processes are handling only high priority items. If a system under not so much high load, you can turn the knob and say, hey, you know what? I'm going to deal with batch jobs or background jobs. Right? So the idea is your system should be able to dynamically adapt to load. Talking about commodity hardware again, the next issue is how do you deal with things failing? Your machine can, like we said ad nauseum, your machine can go fail at any given point in time. The first is we give you gigabytes, hundreds of gigabytes of local disk storage. Any given point in time, in Windows Azure, you can go and talk to local disk and use it. But if you have any valuable data, go take that data and store it into Windows Azure storage, because that is replicated and it's scalable, durable, and so on. For local disk, use it as much as you want, but do not rely on it, because at any given point in time, it can disappear. Okay, in case people didn't see that, I'm going to do that again. Use local disk how much ever you want, but it can disappear at any given point in time. See that? Thank you. So the idea is that your application should be resilient to your hard disk just disappearing. And if your application comes back up, it should be able to restore its state by talking to Windows Azure storage and then restoring itself up. So use local storage as a cache, something which is faster than going over the network, slower than main memory. Distributed systems have transient failures. So you will need to go bake retry logic into your applications. Now, we have kind of gone and done the work for you already. If you go look inside the SDK and you go look inside the storage client sample that we are shipping, you will see that there's a retry policy that you can go specify for your application. So you can say, you know what, if my network connection went down when I was talking to storage, go try it again. Go try it 3 times, 10 times, whatever. Whatever makes sense for your application. But when you're doing these retries between our services or different components of your own services, the thing to think about is be idempotent. You could be retrying several times. So you need to make sure that if you're going to do the same amount of work over and over again, you're just fine. So if you've seen all the the photo gallery, thumbnail demos that we have seen, they are naturally idempotent. I can go write thumbnails any number of times and it will be just fine because the thumbnail is not going to change. But if you're going and processing check transactions or something else which you cannot do n times, you need to worry about this. You need to go think explicitly about idempotency. The next thing to worry about when you're doing retries is to not go and launch a DOS attack, a denial of service attack, on your own service. You would be amazed at how many Microsoft services have done this in the past. We have all learned from it, and these are all things that we did when we were young and foolish. When you're retrying, make sure that you have some logic to go back off and not go take the other service down, because you're just pinging and pinging and pinging and pinging over and over again. Be predictable. You're going to see errors. You're going to see high load, low load. You're going to see your application, a specific web role go down and come back up. You need to make sure any one of these situations, your application behaves in a predictable way. So if you go and ask your developer, or if your manager comes and asks you, hey, this machine just went down, what's going to happen? You should know, well, this is what's going to happen. For that, I have a couple of pieces of slightly controversial advice. The first piece of advice is, don't have any code in your shutdown path. Now, this is interesting, right? As several services inside Microsoft have learned that it is a bad idea to go have any code which relies on being called at shutdown. Because guess what? Once in a while, you don't want to call it on shutdown. So what we learned as a best practice was, instead of having code in shutdown, make sure that your developers always rely on having the plug pulled as the primary way to kill an application. Well, this acts as a wonderful forcing function, because now, instead of having one tester or a couple of testers trying out this one scenario, every single point in time, your developers have to think about this upfront. So we have found that this is a great development practice to make sure that your developers, or all of us, can deal with our application having the plug pulled on. The next is throttle. If you're an application under load, it is at times better to go have a degraded mode of operation rather than toppling over. So if you're under load, you could turn off some features, turn off some expensive operation, just do the basic minimum required to keep your users happy. Now, here's a real life scenario. How many of you here have Twitter accounts? Twitter? Yeah? Okay, I see a few hands. A few months ago, Twitter had a few scaling issues, which they have fixed and they're well beyond now. When they had those scaling issues, they went and turned off specific features of their site. They went and turned off the replies tab, for example. This is a great example of a site or a service which, when under load, is going for a degraded mode of operation just to keep the core service up and running. Now, to tie all this together, I wanted a real-life example and to kind of give it credibility, an example outside Microsoft. So SmugMug is a famous photo-sharing website. They're incredibly popular. They deal with a lot of photos. Now, SmugMug is a classic loosely coupled system. They have a bunch of web front ends which goes and deals with user input. But then they also need to go a bunch of rendering. They also need to go do a bunch of transcoding. To do all that work, they have a bunch of worker processes. Now, here's the interesting bit. To separate work between the two, they have a bunch of queues, but they also have a system called Skynet. Yes, that's right, the Terminator Skynet, which goes and monitors the load on these queues. So depending on the load on the system, it can say, hey, you know what? The system is facing high load. Process only high priority items. System is facing high load. Go spin up so many more worker instances. Or the system is not facing any load at all. Let's go run that bad job we really needed to for some point in time. So this is a great example of a real-life service implementing pretty much a lot of things I've been telling you for the last 5-10 minutes. Another slightly controversial section. When is good enough good enough? What do I mean by that? I want to walk you through a couple of thought experiments. First is, let's think about email. You open Outlook, and you go type in an email, and you hit send. What happens? It doesn't get sent to the other person instantly. The other person doesn't see in the inbox. It gets synced at some point of time in Exchange, and Exchange sends it over at its, whenever it does its thing. And if there is an error, you will hear about it in some point of time in the future, right? The thing is, at no point in time do all people in the system have the same view. The moment you hit send, the other guy isn't seeing the email in his inbox. There is a latency between the two. But it is okay. Email works just fine because of this property. The second is, for some applications, let's say, if you're running a bank, for example, you will need complete consistency and have data accurate at all times. If somebody processes a check, somebody makes a transaction, you want to make sure that every single part of your application knows about it instantly. But let's say you're a different kind of application. Let's say you are Facebook, or let us say you're a social network application, and somebody is processing a status update. Guess what? Not everyone needs to know at that exact point in time. It's okay to have a delay. So what do you get out of the delay? You get better performance. You get better availability. The key here is, in your application, you have a knob. You can choose, here's how consistent I want all parts of my application to be, and here's how, how I want, that much extra performance. Here's an example. Let's say you are going and building a hit counter for your website. Pages have, every time somebody comes and hits your page, you go increment it. If you want the completely consistent way, if you want to know the exact count at any given point in time, what you can do is, you can say, you know what? Only go update the hit counter if it hasn't changed since the last time I saw it. Guess what? Most of us don't care about hit counts being consistent. In that case, what you can do is, just go shard it across. Go split out that hit counter into multiple hit counters. Or go update it once in a few seconds. In that way, you get much better performance because you're not going checking every single point in time. But you don't get the exact answer. But guess what? In this scenario, an approximate answer is good enough. To give a real-life example of somebody having such loose consistency, let's talk about Flickr. A few weeks ago, the Flickr engineers made a blog post called Flickr Engineers Do It Offline. In this blog post, they spoke about their architecture. When you upload a photo on Flickr, your friends will get to know about it, and your friends' friends will get to know about it. But they won't get to know about it instantly. Flickr queues up the updates, and over the next few seconds or next few minutes, all your friends will get to know. But in doing that, Flickr gets to have much better performance, much better availability. So whenever you're building services on top of Windows Azure, you have that knob I spoke about. You can say, I want, when I'm talking to table storage, I'm going to check that E tag I get back. I will not write anything back unless that E tag was the same from the last time I checked. Or the other thing you can do is, you can say, you know what, I don't really care. I'm going to update once in a while, and I'm not going to check whether somebody updated it, because an approximate answer is good enough. Or I'm going to go queue up work. To recap, we saw how we can go build stateless front ends. We saw how you can loosely couple your systems. We saw how you can go build a thermostat in your application. We saw how you can go retry on failures. And we saw how you have a choice between consistency and that much better performance. And that brings us to the end of Act 1. What's the first thing that happens once you have a build out in the cloud, or when you have a build of a new service? The first thing that happens is you go find a bug and you go make a fix. You go update it. So that's what Act 2 is all about, updates. Updates are really hard. There are a lot of scenarios that could go wrong when you're updating. For example, the first thing is, when you go make an update, very typically you run into an issue. You have a bug that you just go found about, or there was an inconsistency, or there was some other issue and you want to go roll it back. Now, it's really hard to go do that, because you already flipped the switch, data is coming to the new service, you have some data in your new schema, it's really hard. The next is, unlike a typical desktop application, where you have just a DVD which you can just send across, or an MSI which you can send across, on the web, you have to worry about both code and data. You have to worry about keeping them both in sync. So how do you do that? What we recommend is, you take code, you take data, and you go update one at any given point in time. Here's how we go do it. Let's say you have N version, okay? You have a specific version of your code talking to a specific version of your data. Let's say you want to go update code. When you go update your code to your newer build, make sure that you can go talk to that older data schema. Make sure that you can either upgrade that older data or just deal with it. The other way is to do the other way around, which is update your data schema and make sure that your code is compatible. And talking about compatibility, at lots of times, your service is going to run multiple versions. It's going to have both versions, your current version, your newer build, maybe an older build running. So you need to make sure that you are backwards and forwards compatible at any given point in time. So how do you do that? The first is, since we have no enforced schema, your code could just be fine. It could ignore the pieces that it does not understand. It could say, hey, this object entity over here in this table just looks like this other entity that I know about. And they might have added a few little properties over there, but I don't really care. The other thing you could do is to go use version numbers in your schema. How do you do that? So here's a typical table schema on top of Windows Azure tables. So you have an employee entity with a job title property, right? It has some partition key and row key. We don't really care about that. Lower down, you see a link query, which goes and looks for a specific employee, in this case, Steve Marks, and it selects the employee out. Let us say that you want to go update the schema on the cloud, and you don't want to go update code. So what you can do is to go add a version number property. Here's how that would look like. You go add a version number property to all your entities. So here you see public int version. That's about it. And in your query, you can check for the version of the property that you understand. So you can say, I only understand until version foo. If it is not version foo, I don't know about it, so I'm not going to go deal with it. And this query will get you only versions, in this case, of version 1. Here's a key problem that we all deal with. How do you do upgrades without having any downtime? You can't atomically flip a switch over to go with your new build. In Windows Azure, we spend a lot of time thinking about this. And we have something we call rolling upgrades. Yesterday, I'm not sure how many people saw Yusuf Khalid's talk yesterday. He went into great detail about this. Let me give you like the Cliff's Notes version. When you go model your service on Windows Azure, you can say, hey, my service is built up of these update domains and these fault domains. So what is an update domain? Let's say this room is my service. And let's say, I want to get a different set of people into this room. That's an update. Well, I love you all and you all love me. So, but let's say I want to get a different set of people. I can say each one of these sections is an update domain. So instead of having to send you all out and feel very lonely until the next batch comes in, I can update section by section by section. In code, you can say that, hey, this part, these specific components need to be updated. And once they have been updated, these parts need to be updated. And then these parts need to be updated. You can do the same with something we call fault domains. You can say that these components need to be split across multiple racks. So if one rack goes down, they'll still stay up on the other racks. This is something we use internally every day. Our storage system, our fabric controller runs on top of these services. For PDC, we are releasing a limited form of this, something we call swap. You saw Don and Chris do this on stage. Here's how it works. You go build a staging version of your application. When you have a build that you want to push to production in some point of time, you go deploy it to staging. You already have a production version running. That is running at your www.yourdomainname.com. When you want to make the switch, you go to the portal and you go say, swap these two instances. And what we will do within a matter of a few seconds, and this is something you saw, is we will go make the necessary network adjustments to make them point to each other. So all of a sudden, your www.foo.com is now pointing to what was previously your staging build, and your production build is now running on staging. And now you can update at any given point in time. So this is a great way of doing updates without having any downtime. Because at no point during even those 30 seconds will any of your customers see any downtime. They will either hit the staging version or production version, and then after 30 seconds, it will only be production. If you have big changes, if you have large incompatible changes that you absolutely need to go take down your servers for, you cannot have both versions of your servers running at the same time. Or let us say that you don't really care about downtime. You only have 5 customers and they're probably asleep at that point in time. You can go stop and start your application. So you go to the portal, you say stop, Yeah, and then you start with the new version up and running. So you have a choice of doing either of these to go have a seamless upgrade. Now, like I said, we have a rich model of how we can do updates and how we can roll out services. So in the future, we will expose more of this model out. So you will have precise control over how your application does upgrades. You can do all the update domain and the fault domain, and you can tap into all that power. Here's a little insider insight. When is the best time to go update a service? Well, the right answer is there is really no good time to update a service, because at any given point in time, you're going to have customers who are hitting your service. But when we went and looked at all our data center logs a few years ago, and we saw that at one particular section of time every day, our network traffic would just go drop down and come back up. And this was across our data centers, which are running a lot of services which are being hit across the world. So it was not as if one particular country was asleep. So when we looked at the data, we found out that this was a time when the sun swept over the Pacific Ocean. So this is the time of day when pretty much every service around the world has the least number of users. This is a time of day when pretty much every data center around the world sees the least network traffic, so the intertubes are clogged the least. And this is something that you would want to go think about in terms of upgrading your service. So this is like a little insider insight. Now, to show you that I'm not smoking something, here's a real-life example of how somebody is using these principles. Windows Live ID. You all know about it. In fact, if you use the PDC website, you're probably signed in using Windows Live ID. As you can imagine, having high availability for Windows Live ID is critical. People not being able to log into Hotmail, people not being able to log into MSN Messenger is probably really, really bad. So the Live ID team does the exact same things I spoke about. They don't run on Windows Azure, at least not yet. But what they do is, first, when they go build a new version of their application, they go make sure that it is backwards and forwards compatible. So when they go roll out that build, and if they want to go roll it back, it would be just fine. And all their partners and all the people using the SDK won't be affected. The next thing they do is to go use a rolling upgrade. So using their own internal systems, they go make sure that they go update one system by one system by one system. So this is like a great example of somebody in the real world using the same principles and practices that I just spoke about. So recap. We saw how to make updates to your service, you update either code or you update data. We saw how you should maintain compatibility when you have new version of your application. We saw how you can have versioning in schemas so that when your code can decide upfront what code data it understands and what data it doesn't understand. And we saw how you can do rolling upgrades. And that is the end of Act 2. For Act 3, I found this interesting little story I want to start off with. In December 1996, NASA launched one of its most ambitious missions to date. It was a mission to Mars, and it was the Pathfinder mission. So over 8 months later, Pathfinder landed, and it started successfully taking photos from the Martian landscape. But pretty soon, they started running into issues. The Pathfinder robot started resetting every few minutes. And they were not getting any photos at all. And the team back in Houston, and by the way, these are authentic photos, which I pulled from NASA's website. The team back in Houston was frantically debugging, trying to figure out what had gone wrong in their software on Mars. They were fortunate enough that they had left all logging and tracing turned on in their final build that they had shipped over to Mars. Boy, that sounded weird. So they could go take those same trace logs, and in their own simulator, they could run the exact same build that was running millions of miles away. And pretty soon, they found out what the issue was. It was a priority inversion issue. In the earlier version of my talk, I dug deep into what the issue was. Someone actually gave me the right bit of advice into not doing that. And after they found out what the priority inversion was, they did something fascinating. They wrote a bit of code which would go and update that piece of memory where a function was being called with priority inversion turned off. And then they went and did this. They went and sent a patch over from Earth to Mars. Now, let's think about this. You're sending a piece of code over which patches a bit of memory to go modify a parameter to a function call. Wow. Talk about remote debugging. So, several hours later, voila, the application came back up, and it was running beautifully. Now, this is an amazing story, right? I mean, forget what talk this is. Isn't this like an amazing story of engineering and how someone can go deploy something remotely? It's just fascinating. And this is the best intro I could find for my next act. When things go wrong, deep voice. First question is, how do I debug, right? I can't bring Mars over. I can't bring the cloud over. So what we went and did is we went and took all the cloud with all its vapor, stuffed it into an MSI, and put it up for download. So you, in the comfort of your own home, can experience the cloud. Seriously, the SDK, the development fabric, the development storage are authentic, high-fidelity replicas of what's running in the cloud. So you can go build, debug, test your application on your local machines without having to get in the cloud at all. We believe this is super important. And this is not just us. Every Microsoft service internally follows this as a best practice. If you're a Microsoft Internet service, you absolutely have a local one-box replica of your service. The next is the piece which I'm going to tell you what and then why. Go separate code and configuration. Pretty much anything in your code which you might want to go change at runtime, go put it in our service configuration file. And here's how you can go and do that. Here's the two configuration files that you would see in the SDK. At the top, you see the definition file. So you can see that I've gone and defined a setting named color. At the bottom, you see the actual configuration file, which goes and takes a setting and gives it a value. So why is this important? It turns out that in Windows Azure, we have a configuration update mechanism. So you no longer have to go deploy a debug build or deploy a new build just because you want to change one specific API key or account setting or one little thing in a config file somewhere. You go give us this new config file, and we can go roll it out across your service and without any downtime at all. So if you go separate out your code and configuration, separate out things like account secret keys, separate out things like API keys, logging levels, you can then go use our logging configuration update mechanism to just go update them and see no downtime. You can't debug the cloud. It doesn't make sense to be able to attach a debugger because you could be running on thousands of machines. It's really, really hard. So the right way to think about debugging the cloud is to go put logging in. Now, this seems pretty basic, right? Yes, we all know logging. We have been doing printf since Kernighan and Ritchie. Well, what you can do here is when you're building a cloud service and you don't have a choice of remote desktoping into a machine just because there are so many machines and the flow is across so many components, go put in all the logging you can. And then go use the configuration level I just spoke about to either turn on or turn off the logging as you see fit. And here's an example of doing just that. So I have a log level defined, in this case, verbose. And right somewhere else in some other piece of code, I go check that logging level. And I say, hey, if it is verbose, I'm going to do verbose logging. So let us say your site is facing an issue, or you absolutely want to get at that stack trace. You absolutely want to see who's that IP address hitting your machine, or some other piece of info which you would typically want to deploy a new build for. You can go just update the configuration file, use the configuration update mechanism, roll it out across a service, do your debugging, and once you're done, just update configuration and roll it back across. right? So go separate code and configuration. The other interesting property that you get out of separating code and configuration is that your operations team, for those of you who have an ops team, can now have control over the application. They can now go change properties. They can go make fairly big changes without having to involve the developer, the product team, without having to escalate to the developer team. So when you're building cloud services, try as much as you can to separate out code and configuration. When you have logs on cloud services, you will see these logs scattered across a lot of machines. For example, let us say you're writing, who's my current user, or this is the image file I just dealt with. You might deal with it in the web front end. You might deal with it in a worker process. That worker process may process it and send it off to somebody else. It is a pain to go debug the flow across these systems. So one best practice that we use and we highly recommend is to go tag every single piece of log information or anything that would be interesting for you in terms of debug spew with a unique ID. A unique ID could just be a timestamp. It could be a GUID, anything. And with that unique ID, persist that unique ID across your system. So as your data flows across your front ends and your worker roles, you have the same unique ID. So you can just go do a grep of your log file, and you can see all that interesting data. Now, this is something we use. So if one of you goes to our portal, and in the rarest of rare cases you see an error, you will see an actual GUID show up. That GUID is actually exactly what I just spoke about. That is a unique ID that you can then hand over to us, and we can go look at our system and say, hey, guess what? That is that error from that machine, that error from that machine, and can go and correlate across. It makes debugging a lot simpler post-mortem. So how many of you find out if your service is going down because you get an email about it? Well, I see quite a few hands. So, this is typically, when something goes bad, you probably get screamed at, or you get an email, you get a phone call. That's how you find out that something went wrong in your service. How many of you actually know that the service you're working on is up and running right now? 2 hands. Wow. So, what we went and did in Windows Azure is to go and solve that by building an alerts mechanism. So, top level, to find out if your cloud service is up and running, just like how Microsoft services find out where they're up and running, you have an alerts mechanism. So this is in multiple ways. If your worker role hits an error of some kind, if your worker role crashes or there is some other failure, you will get an automatic alert. Now, you also have programmatic control over these alerts. When you go log, if you set the logging level to critical, that will automatically show up as an alert. So you can now programmatically go tell the people running application, hey, something has gone really bad, wake up. Now, in terms of reaching out, we have 3 mechanisms. You can reach out to somebody over email, you can reach out to somebody over IM, and you can send them an SMS message. So you can, on the portal, you can pick which of the 3 mechanisms you want to get notified by. When you're building these alert mechanisms, it usually makes sense to go separate the code generating the alert, figuring out whether there's an error happening from the code generating the alert, because you can go change its logic at any given point in time. So one thing you might want to do is to go stick errors into a table, a queue, or something else, and have some other piece of code which checks that error outside of your service. So if all of your service goes down, this guy can then go figure out and generate an alert. And you can also update this piece of code fairly rapidly. We have found that it is usually a bad idea to go have the code which figures out whether there's an error happening also be the code generating an alert. Finally, the big red button. In pretty much any industrial establishment you see, there'll be a big red button on the wall. This is the panic button. This is the button that you go press when something has gone wrong. In your service, go build the same red button, right? So what you can say that, hey, something is, I have huge load, or I just deployed a bad build, or I have this incredibly bad problem. So I'm going to press this button, and my application is going to go roll back to a known state. It could be degraded, it could not have all its features, but it's a known state so that your application then continue functioning. This is the panic button. You would be amazed at how useful this turns out. However well architected, how well built our cloud services are, we have always found a need at some point of time or other to go and hit the panic button, even temporarily, so that we can throw our cloud service into a known mode of operation. To recap, use the SDK to go debug locally. It's a high-fidelity representation of the cloud. Go use it to go debug. Separate code and configuration, because you can now use our Windows Update configuration update mechanism to go roll out config changes without seeing any downtime. Go have configurable logging, so you can turn up or turn down your logging levels without having to go deploy a debug build. Finally, go use alerts. So when something is going wrong, you get to know about it instantly. And, oh, that wasn't finally. Finally, you have the big red button. And that is the end of Act 3. I have a credit slide, which you can see after the talk, which has the links and the people who have helped me out with this talk. I do have one final story I want to end off with. This grumpy-looking individual is William of Ockham, a 13th century philosopher. He was most well known for this piece of Latin, which I'm not going to pronounce, and the piece of English, which I'm not going to try and pronounce either. It basically was a way of trying and explaining things. It said, if there are two options, a simpler option is usually the right one. Over time, this became a way to go build things. It said, when you have two ways of doing something, go pick the simpler thing to build. So keep it simple, smart people. Which brings us back to this. Keep things simple, simplicity. If you have a simple service architecture, if your whiteboard diagrams are not so complicated, you'll almost always have a reasonably good time. And that's the end. Before I break for Q&A, I have a request. Please go fill out session evaluations because we take it very, very seriously. And thank you. You've been a great crowd. I had awesome fun talking to you. OK, hit me with your questions. There are mics in the aisles. Feel free to line up. Yes, sir.
I enjoyed that very much. Thank you. When you were talking about versioning your data and you showed that code snippet and you added the version property to your data class, that's not a very efficient way of doing it, is it, with table storage? Because you don't have the ability to index against that where clause. So if that data set is large, that versioning is going to be a point of contention for scalability, until such time as, I guess, the Azure table storage gets more indexes.
Yes, so that's a good question. So you are right. So anything other than the partition key or the row key, as of today in the PDC bits, is not indexed. But secondary indexes are pretty high on our priority list. So this is a problem that should go away in the future. But yes, you are right. But pretty soon this would go away.
Can you just, when you say pretty soon, can you give any kind of time scale to when you think that might be? Because that gives us another problem. Without secondary indexes, you're going to have to denormalize data all over the place so that you can query it efficiently. If you had those extra indexes, you don't have to worry about doing that. So if we were architecting applications right now, you're going to make completely fundamentally different decisions about how you store your data and cross tables and partitions and so on when you don't have those secondary indexes.
Yes, so we totally understand that. So I cannot give you a date right now, so I don't want to give you a marketing answer. But this is something which is on our roadmap, and we know how important it is. So this is something you would see sooner rather than later, and that's the best I can do.
All right, thank you very much. Thank you.
Anyone else? Yes, sir.
I'd like to clear something up with that last question. Are we talking about SQL services, or are we talking about Azure storage?
This is about Windows Azure storage.
So why would you put indexes to query that storage when we've been told that that storage is more like, think of it as OS level file store, and any querying and complex things you want to do from a database engine standpoint would be in SQL services? Could you address that?
Wow. Okay, first, I'm going to say that this was covered in detail by Brad Calder, who's sitting over there in his talk. That talk was yesterday, so go see the recording. It spoke about how our storage services work, so he went into great detail about that. But in essence, we have a simple table mechanism, so you can do a form of querying. What we like to think of is SQL gives you the database in the cloud. So it gives you rich joins, it gives you reporting, and so on. But we can do a fair amount of querying using our services as well. But I would highly recommend that you go watch the table services, the Brad Calder's talk, which was yesterday, which was in the same track. I don't remember the exact name. There's also a talk from Niranjan, which was the talk before this one, which would also address the same issue. Does it make sense at all? Does it help? Okay, thanks. Do you have a question? No? Oh, you have a question. Yes, sir.
Yeah, just a quick question on the consuming of messages from a queue. In your example, you showed a program which constantly checked the queues to see if there are any new messages.
Oh, that was a bad idea in a real life. I'm a program manager. I write bad code. If this was a real application, you would probably sleep a while before you check messages, or you would not write what I showed you. That was a code I could fit on one slide, so PowerPoint was my constraint.
Yeah, but do you plan on implementing sort of like you could do an event handler or something like that to just hook up and then get an event to notify them, okay, now a new item had entered your queue?
Okay. Brad, do we have something like that? An event handler for queues today? I can get back to you on that. So we do have in the storage client library that you see today a way for inside .NET code to be notified when there is a message on the queue. I'm not sure how exactly this maps to REST service. I can find out the answer for you offline.
Yeah.
Does it work?
Okay. Yeah, that's fine. Thanks. Thank you.
Okay. If someone else has any other questions, come find me in the lounge. We are a nice set of people. Come hang out with us. And hope you guys all had fun. Thank you.